Alright, welcome back. In this video, we're going to go over mechanisms of arrow pushing. Before we actually get into the content of this video, I want to have a quick conversation. It's kind of like a confidence boost, or you have a test coming up, or you're just having a bad day. Just listen. If you don't want to listen to this, then skip to the timestamp. I'll put it in the description. So, organic chemistry is a difficult subject. I'm not going to sugarcoat it. It is. But I believe it is difficult for the wrong reasons. It is difficult because it is how it is taught in schools, your community college, your university. I have had 4 different organic chemistry professors because I went to community college and then transferred to a university. So I had 4 different professors. Only one of them was decent. The other 3 were god awful. When I took Organic Chemistry B, I had my first midterm and then got the averages for the class. The averages for the first midterm was a 17%. 17! That is basically everything wrong on the exam except one problem. That was the average. And the professor thought there's nothing wrong. He says, I'm just going to curve the class and everything will be fine. And you basically blame the students for doing badly. If the average is 17% among 200 students, you really think it's the student's fault? I don't think so. I think it's how it's taught. So that is where I'm trying to be the difference. I've gotten a lot of comments recently thanking me for the videos and because I'm very helpful and people say I'm really smart. And I really am thankful for that. That really means a lot to me. But I'm going to tell you something. I'm going to admit something to you. I did not get all A's in organic chemistry. I was an average student. But here's the thing. This is what I believe in. I believe the best students, the best teachers rather, are the ones that make the mistakes. If you've been a long-time subscriber, you will notice that I have go over common mistakes students have made. These mistakes are the ones I have made. So I'm telling you so you don't make this in the future, because I made those mistakes. I paid for the price. I paid the price in my grade. But now I'm relaying this information to you to make sure you don't make the same mistake as as other students in my class have done. I don't believe, it's very situational, but most of the time what I've seen is students who've gotten A's can be good teachers. They can be. But I hardly see that because they don't know the mistakes to make. Right, and what to avoid. They just, they don't look at all the other options, all the other angles what a student who got the problem wrong would be thinking, if that makes sense. Now, that being said, you may feel embarrassed or nervous asking a question to your professor in front of the class or you're in office hours about an organic chemistry problem you've been having. I don't want you to feel like that when watching my videos. I do not care how dumb you think the question is, just ask it in the comments. Because I can guarantee you there are other people that may have that same question. Because you're watching my videos because you probably went to class and didn't understand something, right? That's why you're watching my videos. And there's no harm in that, right? Don't feel embarrassed, right? I did the same thing. I went to go look at videos when I didn't understand something, right? It's what smart people do, right? They go to other resources. And I want to be a resource for you. So does not matter how many questions you ask. Go ahead and ask 10 different questions under this video if you want, or whatever video you watch online. I do not mind answering. You can go to the comments section of previous videos. People have asked questions, and I attend to that. I try to make every comment personal. If you say you have an exam coming, I want to give you confidence to make sure you do well, right? My goal is for you to succeed in your career. You are the future of civilization, right? Not these professors. They're about to retire, right? They're not going to be contributing much. No offense to those people, but you, the students, are the future. It is my goal, my destiny to make sure that you will succeed. All right, let's begin. Mechanisms of arrow pushing. So in organic chemistry, arrows symbolize the movement of electrons in compounds. So for example, say if I were to put 2 reactive substances or compounds into a beaker, they will react with one another because of electron movement. But how do we depict electron movement basically on your paper, your piece of paper, on a test? That's why we use arrows. Arrows depict electron movement in reactions in organic chemistry. There were 4 different instances in when we would use arrows to depict electron movement. That would be a nucleophilic attack. Now, I went over nucleophiles and electrophiles in my last video, so please watch that video before watching this one, because it's going to make your life so much more easier. The second way is loss of a leaving group. The third way is proton transfer. And the fourth way is carbocation rearrangement. So we're going to go over all of these, then we're going to do some practice problems, and then we're going to do a mechanism together. All right? So here's the general format of arrow pushing. What these arrows symbolize is the electrons moving to its destination. Okay? So let's go over the first instance, a nucleophilic attack. A nucleophilic attack is when a nucleophile attacks an electrophile. Now, if you don't know these two terms, once again, please watch my last video. It is super helpful, I promise you. So, in a nucleophilic attack, when a nucleophile attacks an electrophile, most of the time, the nucleophile will merge with an electrophile, making a new compound. So, let's look at this example right here. The nucleophile, this bromine, is going to attack the electrophile, right? This carbocation right here. And when this happens, the bromine will now join with the electrophile. So notice this electrophile looks like this triangle here. So we still remain this triangle, but now we're adding on a bromine. So we add a bond and the bromine. And this is what a nucleophilic attack is. Basically, 2 components joining together and merging, creating a hybrid. That is what a nucleophilic attack is. So you take all the components of the electrophile and combine it with the nucleophile. So everything in the electrophile stays the same, but we just add the bromine and its respective bond, right? Because bromine just can't be floating around, right? It has to be connected. That is why. Sometimes it can require 2 arrows. So this oxygen will act as a nucleophile and attack the carbon. But carbon can only have 4 bonds. It already has 1, 2, 3, 4, right? There's a double bond here. We can't just add this component onto here. Then carbon would have 5 bonds. That is illegal. So sometimes electrons need to rearrange. In organic chemistry, think of oxygen as an electron bank. It likes to hold on to electrons. So double bonds or bonds are basically invisible electrons. So these bonds here are invisible electrons. Each bond you see, every line you see is 2 electrons. Okay, so right here, this one bar right here, this one bond is technically 2 electrons. So what we can actually do is this nucleophile will attack this carbon, but you'll notice that there's a bond here, there's a double bond. What we can actually do is make this double bond, well, one of these bonds here, collapse into electrons and have it join onto oxygen. So now the oxygen will be single bonded and the extra bond got converted into electrons, which oxygen will hold on to. This makes it able for the nucleophile to bind onto the electrophile. Okay? So now this nucleophile is now a part of the electrophile here. Right? So this molecule is the exact same thing as here. Okay? Now, you may be wondering, can't this be the nucleophile and this be the electrophile? Because you can see that there's a carbon here and the chlorine and an oxygen. Why is this not the nucleophile? It's due to inductive effects, which we went over in the last video. Right, there's a carbon here, but this chlorine right here is sucking up all the electrons. Right, it's sucking it all up in this direction. This makes this carbon partially positive. And remember, partially positive atoms act as electrophiles. That is why. All right. The second way is loss of a leaving group. Sometimes groups need to leave because there is either no space on the compound or the compound is not stable. Typically, the more charges a compound has, the less stable it is. So think about a relationship, right? A relationship has many components to it, right? Sometimes it just doesn't work out. And what will happen is that one member of that relationship will leave. But it always turns out for the better. You don't want to be in an unhappy relationship, right? If someone is unhappy in a relationship, usually the best thing is just to leave, right? Because it'll just make things a lot more worse, right? You don't want to be in an unhappy, sad relationship where your partner is unhappy, right? So that's what a loss of a leaving group is. So look at this molecule on the left here. Look how many charges it has. It has 1, 2, 3 charges. It's pretty unstable, right? But there's a way we can make it more stable by basically rearranging the electrons. So this oxygen is holding 3 pairs of electrons, right? So what we can actually do is kind of reconfigure this. So we can move one of these electrons here to create what would be a double bond, right? But then that would mean nitrogen has an extra bond, right? Because nitrogen can only have 4 bonds, right? 1, 2, 3, 4, right? And if you were to add a different one, another one right here, that would be 5, and that's not allowed. So one of the bonds must dissociate somewhere. It won't be this one because it doesn't have the ability to leave. It's going to be this one, right? This double bond here, right? Double bonds, whenever you see a double bond, always think it has the potential of leaving or moving somewhere else. Not leaving, I should say moving or being transferred somewhere else. So the double bond is going to transfer here, okay? Right here. Well, that would mean if you had a double bond here, so we're adding a double bond here, we can't have another bond here, right? That would not be okay. That's not possible. So that means that this bond is going to go over here, okay, and create the double bond here, okay, which is right here. It's simple resonance. That's what it basically is, okay. Well, if you have a double bond here, that means this carbon has 5 bonds, right? 1, 2, 3, 4, and 5. That's not allowed. That's illegal. So something needs to leave. It's either going to be the chlorine or it's going to be this OH group. I want to tell you it's going to be the chlorine because the more electronegative atom leaves. Chlorine is more electronegative than oxygen. So chlorine's going to want to leave, right? That's what's going to happen. So what we do is depict it by drawing these 2 equilibrium arrows and showing a subtraction sign, basically, and the chlorine as it is, leaving. So this is telling me that the chlorine is leaving. So then we are left with this molecule right here. So notice the chlorine is now gone, right? That's what loss of a leaving group is. The third way is proton transfer. Proton transfer is when a proton is adding to the attacking molecule or shredded off or deprotonated. It's pretty simple. So what's going to happen is electrons are going to target a proton and basically steal it. So you'll notice that it is now stolen the proton, right? Using the electrons. So using electrons, it's going to steal it. Okay? Now, what is this arrow that I'm drawing here? So if I were to steal this proton right here, right? What happens to this bond right here, right? Something must happen to it. It doesn't go away. Well, these electrons form this bond, okay? But what about this? Well, what happens is oxygen will now have an extra lone pair. So it would actually look like this. It will look like this. So this bond right here becomes the electrons on H2O, right? This is hydronium. It becomes H2O because we stole 1 proton away. So then that means we're left with 1 proton and 2 protons and an oxygen, that's H2O. And then since this bond goes away and becomes electrons, it's right here. It can also be used to deprotonate. So sometimes molecules or compounds will just want to shred off a proton and have electrons instead. And that's what's happening here. We basically just shred off this bond right here, and we show it right there by a subtraction sign and the proton here. And we just draw what's left, right? So this bond dissociates and becomes into electrons, which is shown by the extra pair right here. Lastly is carbocation rearrangement. A carbocation is when a carbon has a positive charge on the compound. Now this is very, very, very important going forward in your entire organic chemistry career here. Carbocations have stability. When there are more R groups on the carbocation attached to the carbocation, it is more stable. So an R group is anything that's not a hydrogen. So you'll notice this right here, this carbocation has 1, 2, 3 hydrogens attached to it. Okay. This one has 2 hydrogens attached to it and 1 R group. We call this a primary carbocation or first degree carbocation. It's primary or 1 because it has 1 R group. And this is more stable than this. Okay? But what's even more stable is 2 R groups. So this could be like an oxygen-oxygen, a nitrogen-oxygen. It could be anything that's not a hydrogen. So if there's 2 R groups, it could even be a carbon. We call this secondary, okay, or second degree. And it's secondary because we have 2 R groups. And this is more stable than a primary. A tertiary is when we have no hydrogens at all. That's all R groups. So this can be all carbons, it could be oxygens, it could be whatever. It's tertiary or third degree because we have 3 R groups. Okay? And that's the most stable. So what's going to happen is sometimes protons or methyl groups are rearranged on the molecule to make sure we can achieve the most stable conformation. Okay? So here there are 2 types. There's something called a hydride shift and a methyl shift. A hydride shift is when a proton rearranges itself in its own molecule, right, in its own compound, to achieve a better stability. This is not the same as a proton transfer. A proton transfer is when we steal a proton from something. We're not stealing anything here. We're just moving it around. So here we have an example, right? We have a carbocation right here. This is a secondary carbocation because we have an R group here, right? Because remember, this is not a hydrogen. It's not a hydrogen. This is a carbon right here. So this is an R and this is an R. So this is a secondary carbocation. So what we can actually do is move this proton, so move the bond over to where the carbocation is, and we draw it in like here. But that means that now this is now missing electrons, meaning it's going to be more positive because electrons are negative. So we get rid of this, right? Carbon, this carbon right here, right? It had 4 bonds, right? It had 1, 2, 3, 4, which is great. But now it has 1, 2, 3 bonds. This carbon right here, right? This carbon right here. So we have a plus sign, right? A positive sign. But this is more stable because look at this. This carbon is an R group here, an R group here, and an R group here. This is a tertiary or third degree carbocation, so it's more stable. So we like this, right? Because we've gone from a secondary to now a tertiary by just moving this proton around. So it is more stable. So this is the more favorable position. We could also do the same thing with methyl groups. Instead of a hydrogen, we can actually move the methyl group around. And it's the same deal, right? This was a secondary carbocation. Now it's going to be a tertiary, right? Because we have carbon right here, R, R, R. And we basically just move this to where the carbocation is. And that is a methyl shift. Another way you can think of carbocations is a hole. Imagine you're hiking and there's a dirt hole on the ground. And you'll notice it's kind of unstable, right? If you were to step near it, it could crumble. So what you decide to do is grab a shovel, and you decide to take some dirt in the surrounding areas and fill that hole to make it more stable. But doing so, you created another hole because you were just digging dirt to fill up this original hole, right? But the new hole that you created is more stable. It's not going to crumble under pressure. That's what carbocation rearrangement is. It's basically electron holes in a molecule. And what you're just doing is filling them up. You're creating a different hole, but it's more stable. So let's do some practice problems. Identify the arrow pushing method shown below. So here we have an arrow going from this bond that connects a proton going to this carbocation ion. So what is this? This is carbocation rearrangement. This is a hydride shift because we are shifting this proton over here and we're making a different carbocation ion. Yeah, it's not more stable, but this is the example, right? We're just moving the carbocation ion to a different location. So this is a hydride shift. Remember, this is not a proton transfer. We're not adding protons anywhere. There's no separate molecule where we're adding protons. We're just shifting the proton from the same compound to a different location. What about this one? So what we see is we have electrons from this oxygen, and it is attacking a carbocation ion. This is the nucleophile because it has a lone pair of electrons, and this is the electrophile because you have a carbocation ion. Right? We're not rearranging anything. This is not carbocation ion rearrangement. This is a nucleophilic attack. Right? Because this right here is not a proton, it's not a methyl group, so it's not carbocation ion rearrangement. It can't be. Right? This is not proton transfer because we're not attacking a proton. Right? This is not loss of a leaving group because we're not losing anything. So this is nucleophilic attack. So what's going to happen is these oxygen electrons are going to attack this carbocation ion and basically form a ring. This is very complicated, by the way. This is very advanced right here, is when a nucleophile attacks its own self, basically. But just all you need to do is identify. You don't need to draw, just identify that this is indeed a nucleophilic attack. What about this one? What's happening here? Well, it looks like this water, this is H2O, right? Turns into hydronium. So this part right here is what we're putting into the beaker, right? If we were to put into a beaker, this is what we put in. This is what we get on the output. So we start with water and we get hydronium. This means that we start with 2 protons and we end up with 3. So we must be stealing a proton from somewhere. And this is what this arrow is showing. This oxygen is going to steal a proton from this molecule right here. So this is called proton transfer. Now this bond dissociates, right? Because these electrons form a bond with this hydrogen here. But what about this bond? Well, it's going to dissociate. Well, not really dissociate, but what's going to happen is it's going to form a double bond right here to stabilize this molecule and get rid of this positive charge. This is not carbocation rearrangement because this bond, right, is not coming from a proton, right? We're not moving a proton anywhere. We're stealing this proton, right? If we steal this, there's nothing here, right? So that is why we move this over to form a double bond to stabilize this. Because this needs to go somewhere. We just don't wipe it away. It needs to go somewhere. And it can't go here because there's a double bond here. So it has to go here, right? And that means this carbon has 1 bond, 2 bonds, 3 bonds, right? And then the hydrogen will be here. All right, so that is proton transfer. So let's do a mechanism. And you're probably wondering, I'm not ready for a mechanism. Trust me, you are. So what if I would tell you, show me proton transfer? What are you going to do here? Well, first you need to figure out what's going to be attacking what. Is this bromine going to attack this proton? Or is the oxygen going to attack this proton? What's going to happen? Here's the thing. Bromine can never have more than 2 protons attached to it. It's not possible. In organic chemistry, it's not possible. You cannot have a B, because remember, if the bromine were to attack this proton right here, it would steal it for its own. But bromine cannot have, it can't be like that. It's not possible, sorry, it would be like, this is not possible. Bromine can't have 2 protons attached to it. It's illegal. So that means the only option is this oxygen will attack this proton right here. So let's draw that in. So we're going to draw the tail starting from the electrons attacking our destination atom, which is the proton. So we are going to steal that proton away. But what happens with this bond? It doesn't just disappear. There's electrons in it, valuable electrons. So what's going to happen is this bond's going to dissociate and turn into electrons for bromine to hold on. So what we are left with is yes. That's ugly, sorry. But yes, let me fix this. I don't like it. That looks better. Okay, now we're left with this. All right? Now, now we're over to say, show me loss of a leaving group. What would you do? So say if I want to lose a water here. So I want to lose a water. I'm going to draw a negative sign and an H2O here. I want to lose water. How do I do this? Well, I can just lose this bond right here. So this bond will dissociate like this. So the electrons will now go to the oxygen and create H2O. So this will just leave, and now we're left with this. And then there is positive charge here. Why is there a positive charge? Well, this carbon, right, had 1, 2, 3, and then hydrogen right here, right? 4 bonds. If you get rid of a bond, right, that means we get rid of those electrons associated with it. That means that carbon here becomes more positive, or less negative, I should say, because electrons are negative, right? And if you lose them, that means it becomes more positive. That's why. Now we have a positive charge. I want you to show me carbocation rearrangement now. What would you do? Well, there are many options here actually, but I can rearrange it so we can have this methyl group here rearrange. This is just one of the options, by the way. There's many here. We can have it rearrange, and then we can draw it like this. There we go. So remember, this is a secondary carbocation ion, right? So we have an R group here and an R group here. This is a secondary carbocation ion. And what we did is we just made it into a tertiary carbocation ion, right? R group here, R group here, R group here, and here's the carbon. Now it's tertiary. It's more stable now. Now what happens if I want to do a nucleophilic attack with bromine? Right, from this bromine right here, from this bromine. Let's draw that bromine with respective electrons. Okay, so if you want to do a nucleophilic attack, what would you do? Well, the bromine, the nucleophile, because it has a lot of lone pairs, is going to attack the electrophile, which is the carbocation ion here. And what we do is we join them together. We form a bond with bromine. So now we are left with that, and then the bromine is right. Perfect. See, all we just did is added the bromine here, right? We added the bromine right here because it's a nucleophilic attack. And that is it. You just did your first mechanism. If you found this video helpful, please like and subscribe. And until next time, later.